All right, today we're going to talk about specific heat, phase changes, and latent heat. A lot of this we already talked about in the first day, the Gizmos lab we did. So a lot of this should be review, but we have a little bit more information to talk about, and I want to formally go over it. So make sure you have your notes, if you can, have them out. I'm going to go through the slides pretty quickly. Again, if you want to, just pause the video at any slide you need to take more time on. So specific heat, it turns out that when we add heat to object, different things take more energy than others. And so we have a name for this. We want to call it specific heat. And it's what we studied in that first lab whenever certain objects made our ice colder or hotter than others. And it's because they had a different specific heat. Each object has a different resistance to changing their temperature than others. Each object has, if they have a bigger specific heat, they have more resistance to change. Like water has a very high specific heat. It takes a lot of energy to change 1 kilogram of temperature of water than it does maybe like gold, which gold has a very low specific heat. It doesn't take a lot of energy at all to change the temperature of gold. And we can use this in this equation, Q equals MCAT. Q is the amount of heat in joules added to the mass. So Q is the amount of energy, the amount of heat in joules. Joules are a unit. M is our mass. It's generally in kilograms, but in the worksheet, I believe is in grams. And so the main thing here is we actually can work in grams of this unit. Your M just needs to match your C. So if you have a C that says like 0.129 joules per gram degree Celsius, okay? So if your specific heat is measured in grams, you need to make sure that your mass is also in grams, okay? They just need to match. As long as they match, you're okay. If they don't match, the easiest thing is convert your mass. Convert your mass to grams or kilograms respectively. So match your C always. On the test, I will not mismatch your items. So on one of the homeworks, on the main homework with Q equals MCAT, there were some mismatched C's and M's, which is why maybe your numbers were off by like 1,000 or something, but like you had the right numbers. That's why. You just need to make sure you match your mass. But on the test, I'm not going to do that. C is your specific heat, and then delta T is your change in temperature. If you don't remember how to do change in temperature, change in T is equal to T final minus T initial. Any change is just equal to the final minus initial. Okay, here's some specific heats of objects, just so you know that you can see the different specific heats. They're kind of written funky. I do want you to write them down. Go ahead and write this down on the sideline of your notes somewhere, because we're going to go over an example later where we talk about these three: steam, water, and ice. Okay. Okay, so make sure you have steam, water, and ice is all their specific heats written down. And notice steam, water, and ice are like, they're all the same thing, right? Ice is melted water and steam is evaporated water. But even if you're in different phases, you have different numbers. You can see that we have different numbers for all three of these, okay? So again, Q equals MCAT. The main thing, the hardest part of this problem is the Q. Make sure that if you are gaining heat, if your object is increasing in temperature, if it's gaining heat, that Q is going to be positive. But if you're losing heat, if you're giving off heat, if you are losing temperature, you should have a negative Q. Okay. And it's an important note. Specific heat is measured at constant pressure. It just means we need to keep the same pressure, and we normally use standard temperature and pressure. It's basically just whatever we live at. That's our standard temperature and pressure. There is a specific numbers to it. It does change if you don't do that, but we don't have to worry about that too much. So calorimetry is what we studied that day. Whenever you guys had the metals and you're putting in the water, that's called calorimetry. We put something of one specific heat that we don't know into water, which we do know. We know water specific heat is written right here. We know it really well. And so we can use the change in temperature of both objects. So we can measure the temperatures before and after. We can use the specific heat of water, and then we can use the mass of both. So we need to make sure we get the mass of both the whatever object we're trying to find the specific heat of. And we also get the mass of the water. And we use all that information and use it to find the specific heat of the other object, which is what we did. And there should have been in that lab, kind of a tutorial on how to do it. And the main idea here is that we set the Q's equal to each other but opposite signs. Because if you have a hot metal object in a cold water, that Q, the Q of the water is going to be positive, right? Because it's going to gain heat from the metal. And then the Q of the metal, of some, X, some culprit, whatever we're talking about, whatever the metal is, it's going to lose energy because it's going to give it to the water. That's why it's a negative sign. But the energy has to be the same because energy can't be created or destroyed. It has to come from somewhere, so they have to be equal to each other, just with opposite signs. And we use it we basically make some sort of vacuum kind of chamber such that there's no heat getting in or out. We can get pretty good at this, especially when we have the right tools and the right metals and everything to make sure that no heat's getting in or out. And then we get some sort of thermometer, so we're measuring the temperature of time, and then we can stir to make things go faster if we want to. And generally, you want it to go fast because no system is perfect. We are going to lose some heat, but the faster we move the thing, and the faster we can get the change to happen, the faster we can get the final measurements, and the less heat we lose to the outside world as possible. And so if you want to see examples, I won't go over this example here. Go through the notes, go through the gizmos. They go step by step with you. We also have phase changes. This is a new thing. You probably heard of this before, obviously. So we can have substances that melt, they can freeze, they can boil, they can condense. And then we also have sublimation as well as going backwards from that. They're all phase changes. If we're just going from solids to liquids to gases or back and forth, we have phase changes. And what happens, I'll explain it in a second. If you want to see a little picture, here's all the words. If we're going from liquid to solid, we're melting. And if we go backwards, we're freezing. Liquid to gas is vaporization, and then backwards condensation. Sublimation is solid to gas, and deposition is going from gas to solid. And then if we introduce plasma, if we're going from gas to plasma, we're doing ionization, and if we're going from plasma to gas, we're doing deionization. Sorry about that. So we have a graph here. We can see so this graph is showing as heat increases, what's happening to our temperature. Well, obviously at first, if we're at negative 25 and we add heat, we're going to get to some new temperature. We're just going to increase our temperature, right? We're just going to go up. But eventually we reach the melting point of water, right? 0 degrees Celsius is our melting point. So what happens is we add heat, but we don't change our temperature. At the melting point, we will add heat, but we won't be changing the temperature until we fully melt the water. Once we fully melt the water, and it's now all water, we will start increasing the temperature as we increase heat. Up until a point, again, once we reach the evaporation point, 100 degrees Celsius. It's at that point that we're going to increase heat, but not increase temperature again. At the evaporation point, our temperature doesn't change, we just increase heat. And then once it's all evaporated, it's all steam, then we will increase temperature again forever until maybe we turn into plasma. But we're not going to worry about that in our course. Okay, so we have this term latent heat. So what's happening is, I told you before that whenever we increase heat and we add heat to an object, we increase temperature, right? And what temperature really is all the molecules, all the atoms, they're like shaking, they're kind of vibrating, right? And the more we increase temperature, the faster they vibrate, the faster they move, and that's kinetic energy. And that's what temperature really is. It's just the average kinetic energy of all the atoms. Well, at the melting points and at the evaporation points, at those points where we're doing phase changes, we actually aren't changing the kinetic energy anymore. We're changing the potential energies of the atoms. And what potential energies are, you don't really need to fully understand that. You just need to know that there's some sort of stored energy in the particles that is being increased. Some sort of stored energy. It has to do with the molecular forces, between the atoms and between the molecules and everything. So you don't have to fully understand that. We're not going to go into that deeply, but you do need to know that at the at the phase changes when we increase temperature or decrease temperature, we're either increasing or decreasing the potential energies. Okay. And we call the heat at the phase changes, we call it latent heat. We just give a special term to heat added at phase changes. So when heat is added at a phase change, we call it latent heat. Okay. Because it's energy being added to potential energy. Okay. And we have a couple equations for this. The first one for heat of fusion. So fusion is when we're talking about the liquid to solid phase. It's equal to Q, or Q is equal to MHF, where HF is our latent heat of fusion. It's all, you might also see the equation Q equals MLF. And that's the equation we're really going to use. I like writing L. They mean the same thing though. So the L and the H, they mean the same thing. Okay. We also have heat of vaporization. Obviously, heat of vaporization is the other one, right? And when we're going from liquid to gas. When we go liquid to gas, we have some sort of heat, some latent heat. And it looks like this. Again, we're going to use the equation L. The heat of vaporization is equal to the M times the latent heat of vaporization. It's a pretty easy equation. It's just whatever heat you need is equal to the mass times the latent heat. Okay. And so we have some good ones to know. You should mainly note the water one. All the other ones you would be given to on a test, and including the water one will be given onto the test, but we're going to use this as an example here. So you don't need to memorize any of these. Please don't spend your time memorizing these. Anything will be given to you on the test. But for now, go ahead and write these down because we're going to use these in a second. So you need to know that at the melting point here, for this example coming up, the latent heat of fusion is this, and the latent heat of vaporization is this. Okay, so let's do an example. Let's say I want to know how much heat is needed to change 300 grams of ice at negative 30 degrees Celsius to steam at 130 degrees Celsius under standard pressure. Let's talk about what's going to go on here. We just like that graph, we're going to increase temperature from negative 30 to 0. Then we're going to do a phase change. Then we're going to increase temperature again so we get to 100. Then we're going to do a phase change. And then we're going to increase again to 130. Okay. And so there's actually 5 parts we have to do. This is a 5-part problem. All the individual parts are pretty easy. The hard part is just we have to do all of them. It just takes some time. And so let me get a calculator out real quick. Okay. So what do we need to do? First thing, let's do going from negative 30 to 0 degrees Celsius. So we're going to do them part by part. The first part is going there. What's happening there? Well, that is ice. That's all ice, right? Before we get to the melting point, it's all ice, which means that we're using this equation, Q equals MCAT. I want to find the amount of energy needed, the amount of heat in order to get it going from negative 30 to 0. And so that means my mass is 300. My C is, well, what is my C of water? I think we have it written down funky. So we actually have it written down in, I think we have C is equal to 2.09 times 10 to the third joules per kilogram degrees Celsius. And remember that we need to change this to, that means we need to change our mass to kilograms. So let's go ahead and do that first. Before we do this, let's make it equal to, what is 300 grams to kilograms? Well, we just divide by 1,000, and so we get 0.3. Our C is 2.09 times 10 to the third. Our change in temperature is 30 degrees, right? We increase 30 degrees. And so we multiply those all together. 0.3 times 2.09 times 1,000 times 30. I got an answer of Q is equal to 18,810 joules. And that's the heat it takes for us to get to 0 degrees Celsius. So part 1 is done. I'm going to write that on a sheet of paper separately. And so that way we can do the next part. Okay, part 2. Ask for, well, now we need to go from 0 degrees, now we need to go from ice to water. So now we need to melt. And remember, we use the equation, the heat of fusion. Our mass is 0.3 kilograms, and our latent heat of fusion is 3. Let's see if this works. 3.33 times 10 to the 5th. So again, type that into the calculator. 0.3 times 3.33 times 10. 1, 2, 3, 4. And I got 99,900. So 99,900. I'm going to go ahead and write that down as well. We can do part 3. Part 3 is going from 0 degrees to 100 degrees. So Q is equal to 0.3 times, now we're at water. We melted, and so we need the latent heat, or we need the specific heat of water. And then we need the change in temperature. We're going from 0 to 100, so we're going 100 degrees increase. So we can do that, 0.3 times 4186 times 100. And you should get this as your answer. Q equals 125,580. So 125,580. Okay. Step 4 is now we got to go from water to steam. So we need the Q of vaporization is equal to the mass times the L of vaporization. So 0.3 times, what is it? 2.01 times 10 to the 3rd, which is equal to, let me do that real quick, 0.3 times 2.01 times 1,000. Let me make sure we have that number right. That seems small, but it could be correct. Let me just make sure I have my number right. No, I have my number wrong, don't I? Latent heat of... Yes, okay, I wrote down the wrong number, right? I need this number. That is my steam number, right? Okay, so I need 2.26 times 10 to the 6th. That is the number I need. So 0.3 times 2.26 times 10 times a million, essentially. And we get, that seems a lot reasonable. It actually takes a lot of energy to evaporate water, which is why it takes so long to boil stuff. And then lastly, Q equals MCAT. And so this is for our steam. Our steam is now evaporated. We want to change our temperature to go from 100 to 130. And so the amount of energy that takes is equal to 0.3 times our specific heat, 2.01 times 10 to the 3rd, times our change in temperature, which is 30 degrees. And so we can type that in, 0.3 times 2.01 times 1,000 times 30. And we get 18,090. And then now with all those energies, we finally figured out all the different parts, so we just need to add them all up. So let me do that. 810, because that was the first one, plus 99,900 plus 125, 580, plus 678, 000, plus 18,090. Add them all up. The last one, hold on, my bad. You should get 940,380 joules, and that's the amount of heat it takes for us to get from -30 all the way to 130. And then lastly, there's just a point here. The difference between evaporation and boiling. Water just basically it just doesn't naturally, when it's on the surface, water's evaporating, but at the bottom, when there's bubbles, at the bottom of a liquid, we call it boiling when it vaporizes at the bottom of a pan. So, is this important? I'm not gonna test you on this, but it's on the slideshow, so I thought I'd point it out. It's in your notes. All right, with that, we're gonna go over one more slideshow real quick. It should be pretty quick. I don't know how much of the equations we're actually going to use here. We may use it a bit next class, but I don't think we're using it today. But let's go over the laws of thermodynamics real quick. The first law is basically an equation. Delta U is equal to Q minus W. So delta U is your change in internal energy. If you remember that first day of notes, we talked about that. We can't measure the internal energy object, but we can measure the change, and that's what this equation is. We find the change of internal energy. The change in internal energy is the amount of heat added to a system minus the work done by the system. Okay. So delta Q is positive when there's an increase in energy, and that's negative when there's a decrease in internal energy. Q is positive when heat enters the system, and is negative when heat leaves the system. And then W is positive when the system does work on the surroundings, meaning it's giving off energy, and it's negative when the surroundings do work on the system. Okay. And this is mainly used when we're talking about gases. The second law of thermodynamics says that entropy is always increasing. The best way to think about this is just every system has a state it wants to be in. It has a natural tendency as something that it wants to go to, and everything is always going towards that thing. Everything's always increasing in disorder. Everything's going towards the way it wants to go. Falling leaves want to scatter. Dishes want to break. Ice wants to melt. All these things, it has a general way it wants to go. And another natural thing is that we talk about this a lot when we talk about engines, okay, and processes. It's a lot harder to move heat out of a cold place than it is to take heat from a hot place to a cold place. So we already know that heat likes to go from hot to cold. This is what the natural tendency is, and this is the natural direction of the world. This is what an entropy is increasing as it does this, and generally it doesn't want to go backwards, but it can go backwards, but work must be done, and it takes a lot of work for us to go backwards, which is why your refrigerator and your air conditioning unit are some of the most energy consuming things in your house. They take a lot of work to make things cold, but we can do that. A heat engine is a device that absorbs heat from a reservoir at high temperature and converts some of the heat to work and expends it to a heat reservoir at a lower temperature. So we can make things cold by using a heat engine. And then the law of thermodynamics says it's actually impossible to reduce the temperature of an actual system to absolute zero by any set of operations. The idea here is that, so we can't actually get things to absolute zero. The reason why is because if you have some sort of machine to reduce things to absolute zero, that machine is going to be imperfect due to the second law of thermodynamics. And because it's imperfect, it's accidentally going to always give heat to this object that you're trying to reduce. And so no matter what, you can't get it to zero because you're going to always unintentionally add things to it. There's also a zeroth law. This sounds fake. This sounds like I'm making it up, but no, it's real. We called it zeroth law because I guess just after the fact we decided this was important to do. Essentially, it's super basic. It just says that, hey, if two objects are in thermal equilibrium, which means same temperature. If you don't remember, that means they're at the same temp. And then also if A and B, wait, no, so this is, oh, my bad, the way it's phrased. If A and B are separately in equilibrium with the third object C, so that means A is equal to C, and then B is also equal to C. That means that A is got to be equal to B, right? Essentially, if A is equal to C and then B is equal to C, that must mean A is equal to B. It's kind of a weird thing, but it allows us to find temperature. So it's kind of an important basis, even though it sounds so simple. It has to be done in order for us to establish a basis for temperatures. That's really it. You can expect questions like this on the test, but you can expect like direct recall. Like I'll say, which law of thermodynamics talks about entropy is always increasing or something like that. And you should know, I'm talking about second law. I might tell you which law of thermodynamics talks about how we can't get something to be absolutely zero. And you should just know third law. So it's really recall here. There's not much more in depth we're going to go in this course. With that, I'm done. Have a good day.